Hi, and welcome to our poster, Simulating the Immune System Response to COVID-19. Why do cytokine storms develop and preventing this fatal condition? I'm Rafat Zaini presenting on behalf of my collaborator, Ken Cooper, who is a pioneer and advocate for modeling human systems through his work in HIV modeling. This modeling work aims to understand better how the immune system's response to COVID-19 and how the often fatal phenomena of a cytokine storm develops and ultimately how to prevent it from happening. If you're familiar with the house medical TV drama, our model is a house style model for constructing what is happening or could be happening to COVID-19 patients. So, what are the cytokines? Cytokines are strong chemicals the immune system releases to gear up an immune system response to be faster and more robust in battling any antigen, including viruses such as COVID-19. The escalation of the response is needed. However, not enough cytokines induced activities and the virus continues and worsens. Too much cytokine response and it became a cytokine storm. The major factors and their interactions considered in this model include 5 stocks, and I'm zooming in here to show them to you. They are the infected cells, the cytokines, the T cells, the memory T cells, and the lung damage. When COVID infection takes place, COVID-infected cells accumulate and replicate, causing lung damage. At the same time, or after a delay, when they are detected, cytokines are generated. And when cytokines are generated, they call for T cells. And T cells evolve to become memory T cells and remain ready for future attacks or future infections. Cytokines at the same time could also cause lung damage when their levels go unchecked if there is a delay in the memory T cells and the T cells generation, and the gap would persist. And that's why cytokines create lung damage. Let me show you some model simulations. Initial model simulations show the sequence of events. As the level of COVID virions increases, it is followed by cytokines generation and then the T cells generation. At the same time, there is cumulative lung damage that is happening. Below is a plot that shows how the lung damage is driven far more by the cytokine storm rather than the virus, as we can see in this blue curve showing the virus and this high curve that shows the cytokine storm. Another view from the simulations show what is potentially happening in the race between the virus attempting to invade the body and the T cells trying to kill the virus. We see a surge in the T cell response followed by a decline after the virus is cleared. However, part of the T cells become memory T cells and remain ready to deploy should any new infection start, illustrating how the mRNA vaccine works. To explain how the cytokine storms are generated, we look at an aggregate representation of what could be happening. First, initial infection takes place and the cells are infected and they increase through replication and causing lung damage. With a delay, the cytokines are called to be released, generating more cytokines, and the T cells that are called for, calling for and generating T cells, and depending on their strength, they also kill the infected cells, thus reduce the virus-infected cells. And that's what we call the immune response. If the T cells called for or the T cells did not meet the requirement called by the cytokines causing T cell deficiency, they call for more cytokines to be released and more cytokines, and what we call is upregulation. The high level of cytokines could create cytokine storm in an over-response, causing more lung damage and deaths. The consequences are shown in this chart here of lung damage. We see different manifestations of what could be potentially happening in response to an infection, and they can be grouped into three categories. Either the patient would see minimal lung damage, or they could see permanent lung damage but not fatal, or lethal lung damage that could lead to death. In our search for influential parameters, we identified a number of them through conducting sensitivity tests. They include the time delay in recognizing the virus. If it takes longer, then this could cause permanent lung damage or death. If it is shorter, then there's a possibility for saving the patient. The effectiveness of the T cells is also an influencing factor, and also the speed at which the T cells can proliferate. If the speed is slow, then lung damage could happen. If it is fast, then the patient could be saved. Those parameters reflect different patient conditions and medical interventions that may most beneficially focus on these factors. What we're currently looking for are collaborators, subject matter experts to work with us, sponsors who see both the humanitarian and business case in this work, and coaches to help us make the work better and bring it to where it could potentially be of benefit. Please find our contact at the bottom right corner of the poster, and we look forward to your communication. Thank you from Rafet and Ken.